let me first take a moment to welcome Dr. Khojasteh. I hope I said the name correctly.
Yes.
I call him Mohammad, so it's much easier for me to call by his first name. So, and John calls him Dr. Javed. So, yeah, this is a variety of names. And again, thank you for coming. Ours is a Computational Intelligence Society chapter, which is part of IEEE Schenectady Section. And this has been pretty active. Last year, we had quite a lot of talks. And this year, we are not only talks, we're planning to schedule summer schools as well, working on it. Just to give some background, Dr. Khojasteh is based in RIT. He's an assistant professor in RIT. Did his master's in 2017, and then just 2 years after that, you got your PhD. So that's amazing, and both from UC San Diego, which is a nice place. I had been there actually, so it's beautiful right on the coast. Currently, Gleason endowed assistant professor, right? So you have that that position, and you worked in MIT and Caltech, and also Scripps Institute of Oceanography. This is that I think this institute is in San Diego. It's pretty active in oceanography. Yeah, they even got a Nobel Prize, I think, recently. One of them, if I'm not mistaken. Yeah. So basically, we wanted to hear your lecture, which is really exciting. It has a lot of learning part and controls. And in CIS, we try to encourage, and bring people to know a little bit about AI and the application of that. So if you can tailor to our audience, again, audience at the moment, they're still joining, and just continue to talk. And we'll take some Q&As at the end. Rather than the middle. Okay, thank you.
Yeah.
Welcome again.
Yeah, thank you so much for the introduction. Yeah. So I'm going to share my screen. So am I in the presentation mode? You can see my screen now.
Yeah,
that's good. Yeah. So yeah, I'm the founding director of a lab here at RIT. It's called CAS Lab. We fuse ML, control, and sensing into intelligent system to achieve the result that this field cannot achieve independently. But whenever you want to apply ML to safety critical system, there are both encouraging and discouraging example. An encouraging example is Google data center cooling. DeepMind was able to reduce the billing by 40% by using AI. But there is also like discouraging example, like Boeing 737 MAX 8 crashes in 2018 and 2019, when we have AI, but not enough sensor, and a confused AI caused life loss and billions of dollars of loss in terms of money too. So what we do in our lab to ensure that we can safely do this is that our research strategy is grounded in the deep analysis of the problem, the nature of available data, the specific constraint for each application, and uncertainty quantification also is a big part of what we do in the lab. So we interested in various robotic platform, but for one of our main interests is underwater robotic, because underwater environment are unpredictable and challenging in general, and also common high bandwidth sensor like a LiDAR or camera are usually inefficient in underwater, and we need to rely on acoustic sensor that have low frequency and low resolution. And by the way, this is my student Adam working at RIT with one of our robots, and he just joined Navy recently as an instructor and officer. Yeah. And so why autonomy is important in underwater robotic is that if you work with a surface vehicle, you have wireless communication and GPS. But as long as you go to like shallow water, you need to rely on acoustic signal, and you are going to have bandwidth limitation, and as well as like packet drops. Even you could go to the deep ocean or even like ocean in other planets. And as you go down this road, You have more uncertainty and lack of infrastructure, and autonomous robot system are of great interest. And so, yeah, these are like the platform that we have currently at the lab. It's a USV ROV team with various advanced sensors, and these are the field trial at RIT tape reserve. So this was just like a background introduction about my lab, and today I'm just going to mainly talk about AI and some like theoretical work and algorithms. And let me start with safe learning in robotic. And then when I talk about the Gaussian process and Bayesian learning, how they can help us to ensure safety in robotics. And then I finish with saying some of the drawback of using Gaussian process. And then I talk about the very recent work that kind of address that it uses neural network and it has like efficient uncertainty quantification. And then I switch gear. I want to talk a little bit about sensing and inverse problem and how neural network could help us there too. Yeah, so let's start with talking about learning for robotic. We need to consider two critical points when we want to do that. One is that, so we need to care about both cyber and physical level. And we need to learn online, relying on the stream of the data. Also, we need to ensure control objective and ensure safe operation despite the uncertainty in the learning algorithm. And so basically what I'm going to tell you today is that we want to develop a safe learning enabled planning and control algorithm for autonomous robot system to ensure that we can guarantee individual safety. I mean that we want to ensure that we are able to avoid forbidden areas, and we want to also ensure joint safety, meaning that we want to avoid collision with other robots. So let's look at an example in 2D, very simple. We have a robot here. It just want to go to its randomly chosen goal position, and there is like unsafe set, and the robot doesn't know it's dynamic or there is like uncertainty in the environment, how it can reach its goal position safely. By doing so, we also address the following issue with reinforcement learning algorithm, that they do not provide any formal guarantee of safety. And if you do the training directly in the hardware, it could bring damage to the hardware or harm to the human. So whenever you talk about like an autonomous system, you have an autonomy stack. You have high-level decision making, which is usually work with the grid word abstraction of the word. It runs on low frequency. You could use algorithm like deep reinforcement learning to find, for instance, if it's a mobile robot, the waypoints that you want your robot to reach. And then when you go one layer lower, a little bit more higher frequency, you have a mid-level trajectory planner. You have like your waypoint. You want to find the trajectory that goes between those waypoints. And usually you use like model predictive control. I'm sure many of you have seen like the videos in Boston Dynamics. And many of them, actually, they don't have any learning, and it's just like model predictive control. And then we have like low-level controller when we basically interact with the physical world, and this like controller need to run at high frequency. So for this part of the talk, while in the lab we work in all these like aspects, I'm going to focus on low-level controller when a baseline control policy is provided by higher level decision maker. And the philosophy that I'm going to follow in this part is that of George Box, that all models are wrong, but some are useful. So we're going to do a safe learning enabled model-based control when we do unsafe quantification via Bayesian learning. And we are going to develop efficient Bayesian learning to obtain a distribution over the system dynamic, and then use that distribution to optimize the system behavior. So before going through like the mass, let's look at that very like high level example. We have an Ackermann derived vehicle. And I assume that we don't know its dynamic, and we wanna steer it safely to a goal position. So if you take any like course in robotic, for instance, the one that I teach in RIT here, you are like familiar with this setup. It's basically a very simple geometrical model that represent the steering in a car. And so let's look at these figures. I'm going to show you some like result before we move to the more details. So here the dashed line is going to be the Ackermann-derived vehicle trajectory, and the obstacle are shown in red. And we are going to look at two settings. One is that we are not going to do any learning, and the other one is that we are going to do online learning. With no learning, we are just going to rely on prior system dynamics. And with online learning, we are going to update the estimate using the data that we collected so far.
Mm.
So if you look at these two results, you will see that with no learning, uh, with the prior dynamic, the variance is so large and the safety constraint is conservative and the vehicle is not able to pass between the two obstacles. But in the online learning setting, you can reduce the variance, gather data, and vehicle could safely move between the two obstacles. So in many cases, when you look at such a problem, again, all models are wrong, but some are useful. One of the good system dynamics to look at is control affine dynamics, fx plus gxu. It's nonlinear because f and g are nonlinear function, but if you fix x, it's affine in u. So it's kind of like ax plus b for u. And this is like a good model for car-like robot, for bipedal robot, and for underwater robots too, in general. And so you can write this dynamic as a multiplication of a vector f of x times a matrix big f of x times a vector which has like a 1 and all the other control inputs. And here f is the drift term and g is the input gain. And we want to study the problem of enforcing probabilistic safety when both f and g are unknown. For instance, you could think about like off-road autonomy when you have like a vehicle, it goes from one area to another area, the dynamics of the vehicle is going to change. Or if you have like a Amazon warehouse, you have a robot, you put different load on the robot, the dynamic of the robot is going to change online. Or if you have an underwater robot, it just go to a new area with new drift, with new turbulences, it's going to change. And we need to account for that. And so here we are assuming that these unsafe regions are known a priori, but there are like extension of the work that we have done with some of my former colleagues that you can also look at that the cases that these uncertainties set also unknown and learn their location online too. But for simplicity, let's assume that the unsafe set also is known here. So we are going to put a Gaussian process initial belief or prior on the dynamic. We assume that vectorized version of f of x, so this matrix f that captures the dynamic, when you vectorize it, meaning that if you put like all the columns of f and g after each other, is distributed according to a GP with mean vectorized M0 and covariance K0. And a nominal control policy pi is given to us by high-level planner. And so if you have worked with time series forecasting, you should be familiar with Gaussian process. And it's a universal approximator, and it kind of not only tells you what is your mean estimate, but also tells you how good your estimate is. But this is a little bit more difficult than the time series because it's GP is going to be a function of X state, and a state is going to be a function of time. And so here X is just some point in the state, and X prime is another point in the state. And this function K0 captured the correlation between different location in the state space. So our aim is to modify this control policy pi in a minimum invasive manner during online operation to ensure safety with probability PK. And this PK is a user-specified risk tolerance. So at any triggering or sampling time TK, we are going to solve the following chance constraint formulation. So we want to look at the control input that we want to give to the system that is close to the policy designed by RL or any other high-level planner, while also ensure that safety, which I'm going to define later, how we're going to formalize it, is ensured with the probability at least PK. And PK is the user-specific risk tolerance. If it's for autonomous car, it should be of the order of 10 to the power of -8 to be able to beat humans. That's the accuracy of a human when they drive. But if you look at that underwater robotic, if you look at that agriculture robotic, off-road autonomy, there is no more need actually for learning there because there is less infrastructure, but at the same time, there is more room for error and forgiveness occasionally.
I see.
Yeah, it's a very nice problem and to think
Yeah.
about. Yeah. And so I'm going to just do one slide about like what we have done in terms of learning,
Mhm.
and then a couple of slides also about like how it matches the control. And then I'm going to talk about like the unstructured environment and multi-agent setting before talking about like the new result in neural network.
Mhm.
Uh, so recall that the dynamic was able to be written like this: x dot equal to fx times underline u, and we have a Gaussian process belief, which is like we are going to use a GP for inference. It's a universal function approximator. Not only it gives us the estimate for mean, it also gives us estimate for like the whole posterior, the variance too. And assume that we have a training data set x, which is the state from time t1 to tk, u, the control input from t1 to tk, and the velocity, how a state is changing, like x dot. Uh, yeah, and these are could be like measured either, for instance, using an INS, inertial navigation system, or IMU, or if you have some sort of anchor in the environment that you know its location, you could send a signal like a radar, like a sonar, and like measure your distance, time of arrival distance, and measure these quantities. And they could be noisy too. And in general, there might be correlation between component of f and g, and we have like one set of data, and we want to learn f and g simultaneously. So we have x dot equal to fx plus gxu. We want to learn both f and g. And the state of the art before us was like using Gaussian process that are decoupled to do the system identification. So what we have done is that we find an efficient factorization of this kernel matrix K0 based on Kronecker product of a matrix that is state independent and a smaller matrix that is state dependent. And we designed this in a way that once you do the inference, um, the resulting posterior is also going to have the same form, and then you can use like short decomposition to solve the problem more efficiently. So we extend the concept of matrix variate Gaussian process to this case. And with this way, we model the correlation among different components of the system dynamic, and it have the similar computational complexity, but it has much more greater flexibility in inference. But again, there is going to be some issues in computation time. There are approximation, but more recently, we designed an algorithm that kind of do pretty good in uncertainty estimation, but also it's much more computation efficient. I'm going to talk about it in 5 minutes um, or so. So if you look at the literature of like advanced control theory, nonlinear control theory, or robotic, one of the cornerstones these days to ensure safety is CBF. And they dynamically enforce safety for known dynamics before we do this. And they are based on this function h of x, which has a specific property. For instance, is like always non-negative on the safe set and negative on the unsafe set. And they are defined based on this control barrier criteria, which is the lead derivative of function h with respect to dynamic uh, plus alpha times h. Here, alpha is a positive number, and lead derivative of the h with respect to dynamic is basically just gradients of h times dynamic. And so this is basically looking at the derivative with respect to a vector field generated by motion of the robot in the environment. It looks how h, this function h, is changing along this vector field. So if you have taken any like nonlinear control theory class before or taught before, a nonlinear control class, it's very similar to Lyapunov criteria. And when we ensure that this CBC control barrier criteria is positive, we're going to have a tight lower bound on the derivative that ensure that as the robot is moving in the environment, it always ensure that H stays positive and it doesn't enter the unsafe region.
Mhm.
So with the learning part that I didn't go to all the detail, we obtain a posterior over the dynamic. And recall that we wanted to like solve this problem project the policy to the closest action and ensure safety with probability bigger than PK, a user risk, a specified risk threshold. So now we can like replace this like safety with the control barrier criteria and ensure it to be just positive. And since the dynamic is Gaussian modeled by Gaussian process, it's random. This control barrier condition is also random. So it's going to be a chance constraint formulation. And interestingly, when you assume that you know XK and UK, this criteria CBC is going to be a Gaussian random variable with mean and variance as follow, when mean is linear in U and variance is quadratic in U. So this is very important because chance constraint formulation are usually tough to solve. But because we use Gaussian process here for modeling here, you can actually solve this using the deterministic problem based on the variance and covariance of this control barrier criterion. But when we were like trying to actually solve this in various systems, we noticed that, oh, sometimes it's not going to be solved efficiently during online operation. And this is basically a quadratic constraint program, QCQP, and it might not be convex always. But there is like a famous paper by Stephen Boyd that says that, you know, you can always write a QCQP as an SOCP, and you can solve that efficiently. But I simplified the presentation for this part of the talk a lot. First of all, I only talk about relative degree 1 system, but if you want to solve like a bipedal or car-like robot, or even like more advanced robot like underwater robotic, you need to do higher relative degree system. So if you are interested, we can discuss or you can look at the paper. Also, I only talk about safety, but there need to be another condition added here that ensure liveness using a Lyapunov criteria. And when you have like more conditions, there's going to be feasibility issues to solve this program. And then there is like a principal way that you can sacrifice liveness for safety that we did here. And so let's do a final example here before we move to the multi-agent system. And the more recent result is that let us look at that two cases. When we do mean CBF, when we do not account for variance, we just look at that the average estimate. And when do we do Bayes estimate? Not only we look at the mean, but also we look at uncertainty quantification. And as you can see, when you do mean CBF, the controller does not account for uncertainty and it just make a crash with the obstacle. But when you do Bayes CBF, it slow down, it gather more data, and it safely cross between the two obstacles. So I think the most important thing that I learned from like working in this area is that whenever you want to apply a machine learning algorithm, especially if it's in a safety critical application, we shouldn't just look at that point estimate. We shouldn't just look at that the average accuracy, which people in machine learning usually tends to do. But uncertainty quantification is such an important topic, and like doing that efficiently is very important.
Yeah.
So,
Professor, before you go to the next topic, I had one question which may be important here. If the system is nonlinear, you have this G and you know the other function F, and U being multi input, and X is so many states, right? So, how do you really ensure that it is stable when you're trying to learn and adapt over time? That is one of the biggest problems I've had when I design control systems, especially nonlinear control systems. Very difficult to ensure stability, and sometimes it could go out of bound, right? So
yeah. So, so there are two things here. One is that once you have a nonlinear control affine dynamics, there is like more theoretical guarantees for stability, you know, and convergence than a general nonlinear dynamics. And another part that we didn't discuss actually, it's that you can add additional constraint when you solve that optimization problem. So we kind of like assume that the good policy is already given to you by the high-level planner, pi, and you want to like change that in a minimum invasive manner. But when you change it, you could also got stuck in a point or like make the system unstable. But there is going to be like additional constraint based on Lyapunov criteria. that ensure that the system is going to stay true to the course of the action that has been designed for. And yeah, but when you add more constraint, it's more challenging to solve the problem.
Yeah.
And sometimes you have to sacrifice liveness and staying true to the course of the action to ensure safety.
Yeah.
So,
Yeah.
yeah.
Good. Thank you. Mhm.
Yeah. So let's talk about like navigation on a structured environment. You have a robot blue here that tries to navigate from a start position to a randomly goal position yellow, while avoiding collision with other agents that are shown in red. So approximately half of this agent, we assume that they are blindly travel to their randomly chosen goal. Half of them show some degree of collision avoidance behavior. And in such a case, estimating uncertainty in the prediction of other agent is very important, because and we need to learn and account for those uncertainties. So this is basically an extension of the previous work to kind of a multi-agent system or navigation in a structured environment. For instance, like when you want to have your robot work among human or like working like factory of future, and then there is going to be like other agents that could be like egoist, just go, or they could have like checking their phone or other things, and it's an unstructured environment and you want to navigate among it. And so I just want to show this in very high level. It's a very nice work. A nice problem. I enjoyed it. And you can see this is the left side is sample pass of the multi-agent system based on the state of the art of the control barrier criteria when we don't do the learning and we just use robust control. But the right one is what we did when you do learning too. And as you can see in the left one, the crash happens, but in the right one, it slowed down, gather data about the neighbors, kind of rewrote and safely reach out there. And by the way, when we run many iteration, the left only was able to do safely 85% of the time, but we achieved 99% of the time.
Mhm. I see.
Yeah. So I just wanted to also talk about this more recent work that we done based on like Spline neural network and Kolmogorov networks. So I'm quite excited about. So as I was kind of hinting earlier, uh, Gaussian processes are great, but there is a significant bottleneck because they don't really scale to high dimension and many data. And there are many specific fix and like approximation to do, such as local GP and other, but they also have their own trade-off. And this is like a famous like memes from X, previous Twitter, that says that this is how people believe the world would look like if Gaussian process was scalable. Um, but let's look why Gaussian processes are interesting. And I think one of the most important thing is that they have this property called distance awareness. And to show you that, let's look at a very simple classification problem. Let's say that we have this simple classification problem. We have data in red, data in blue, and we want to classify. So when we want to do the classification, we could have a very simple classifier, like a linear classifier, that says that, this is the red class, this is the blue class. And we could have like a ring classifier. But if I ask you, like, what is this point is going to be classified, the star point in both of these cases, one of the classifiers says that it's red, the other one says blue. Also, it's the same problem, same data, but just a different algorithm.
Mm.
So this is like this sort of uncertainty. In the background, by the way, we are showing uncertainty, and it goes from 0 to 1. And like in the border, here is the most amount of uncertainty. So these two uncertainty classifiers are not distance aware. So what we are looking at and what we are interested is like to have neural network or classifier that, whenever you are close to your data, you classify safely, correctly. Also, you say that, oh, okay, whenever I'm like close to this region, I have low uncertainty. But as far as I get further from the data that I have been observed, I should have more and more uncertainty. So we should have like a kind of uncertainty that decrease
Mm.
and respect the distance from data that you have observed.
Mm.
And the question that I have been trying to answer for a while with colleagues was that Can we develop an efficient and scalable neural network that it also has these nice properties of GP, kind of like respect the distance to the data automatically? And it's a very challenging problem because if you do underestimation, underestimate the uncertainty, you could have unpredicted behavior and it could be very dangerous. And if you overestimate it, it could be conservative and it's going to reduce the performance. But if we need to have like a well-calibrated uncertainty estimation, so we have like nice and clean uncertainty aware behavior, optimal uncertainty aware behavior. And when you think about this problem, like in GP, it's probabilistic, but you can also think about like worst case bound. In case of like probabilistic, sometimes in a specific problem, when we know the distribution, it could be tighter, and the guarantees would be with high probabilities, and it could be like for stochastic decision making and control, and we can use it when the risk is small. You can also think about like worst case bound instead of just like a probability over the safety. You could have like a more conservative approach that consider all possible uncertainties confined in a set. And in this case, you will be in robust control. And in robust or worst case or adversarial, the assumption is that you never want to violate the criteria. So let me talk about like Spline neural network and how we are being able to make a scalable distance-aware uncertainty bound. So we have like two recent paper, but we are going to submit to journal based on these two. And so to get this very well, let's think about like machine learning as a general concept. So we can say that the machine learning model could be classified in three cases. One is going to be a parametric, like MLPs or CNN. They have a number of parameters that could be large, and we have like high accuracy, but they are less interpretable, and they don't have uncertainty quantification that is like built in. And then you could look at that non-parametric one, like such as GP. They are more flexible. They capture the complex pattern, but they are computationally expensive. And I think the key that we find here is that we could look at that somewhat bridging this concept. We look at the semi-parametric model to balance the flexibility and efficiency and have more interpretable learning algorithm. And an example could be Spline. So Spline was very popular for statistical learning in 60s. But then deep learning kind of, because they have like issues in terms of scalability too, and deep learning kind of like dominate everything. But recently, splines have a comeback in machine learning community. So let's discuss about where the spline come from. It originates from the flexible wooden strips used by ship builders, and they are constrained by control points or knots. So I'm going to talk a lot about knots here. So this is where the term spline came from. So assume that we have like a spline. It's going to be a set of polynomial that they are going to be continuous at the knots. And so you can like, instead of neurons in neural network, you can use like a spline as an activation function. And it could be cause something called a spline neural network that has been around from like 80s. And one of the most recent one that has got a lot of attention is CAN. So we are going to look at a spline neural network as a semi-parametric model. So we are going to modify CAN such that the knots are a subset of training data. So we are going to, Spline are going to have knots when you train them, and we choose the knots to be a subset of training data. By this way, we are combining accuracy and computational efficiency of parametric model because it is still a neural network, but also now it's kind of semi-parametric. And because we choose the knots to be a subset of data. So it's kind of in between. And we are going to use this property in this talk to develop a worst case distance-aware uncertainty for neural network. So what we have done in these works is that we look at the spline, we prove the theorem, how we can calculate the error for a spline. And then we look at each of these neurons locally and make the error, calculate the error for them, and propagate this error to have a error for the whole network. So it's instead of like a bottom to up to bottom approach. This is a bottom up approach to uncertainty estimation in Spline neural network. It just kind of go from a neuron to the whole network. And so we find error band for each neuron and combine it using a theorem that we call propagation theorem through the whole network to find the uncertainty. So using this theorem, we designed the neural network like this, that it's going to be made of blocks called PPE, piecewise polynomials error. When you do like prediction, you have data input and output. So this is going to be similar to regular neural network. But at the same time, at each spline, we do interpolation error, and we calculate the error at nodes because we are doing splines with using training. There is going to be error at the nodes too. And we look at the error of a spline, how true function minus or a spline fit is going to have an error based on Lipschitz constant. So we are going to look at the interpolation error, and we are going to look at the error at nodes too, and we sum of all of them. That is going to be the local error at the spline. And the neural network is going to be made like this. Instead of neurons, actually, we are going to have PPE, that at each neuron, it say that, oh, okay, this is my activation, and also this is my uncertainty. And we use the propagation theorem to propagate the uncertainty throughout the network. So when you do the prediction, you have a prediction and you have a confidence at the same time. And this is like, I didn't go to all the details of math, but this is like an example that you could see there is like a true function. There is like ensemble, which is basically mean that you do lots of cans here and Monte Carlo averaging, Monte Carlo simulation. And then there is like going to be GP, which is the Gaussian process. So the point is that ensemble is not going to be distance aware. But GP is distance aware. DAREK is also our method, distance aware error for Kolmogorov network is distance aware. But the good point is that if you look at the computational efficiency, after 500 samples, here the yellow one is ours, DAREK, and then the red one is GP. You could see that DAREK is doing much better than GP in both like training time and inference time. And so I kind of revisited this study for this problem, the multi-agent navigation on a structured environment. And there are like cases that GP make a collision, but the worst case error band that we have that is actually more efficient could safely navigate to its randomly chosen goal. But both like Bayesian method like GP and DAREK, our method, have like hyperparameter to tune. In the case of GP, when you want to look at your confidence interval, you can like say how many standard deviation you want to be inside, like 2, 3, 5, 6. And for us also, you can look at the Lipschitz constant, and we see if we like increase those. In both cases, we can achieve very success rate. And we also, there is some drawbacks in DAREK that I'm going to talk to in the next slide. And because of that, we also developed a new model called KDAREK, and we apply this in real data set too. We applied DAREK in some imaging data set too, but it's still in progress. I don't have it in the presentation now, but we have some like UCI regression data that I'm going to show you how like this algorithm is actually going to work. So DAREK are based on spline neural network. They are hard to train. When you stack splines on top of each other, sometimes in the training loss, you are going to have oscillation. The geometry of like optimization is much more complicated than ReLUs. And there is also lots of hyperparameter to tune. So what I didn't describe, and I want to mention more, is that in the propagation theorem for going error from a neuron to the whole network, we need to assume that Lipschitz constants are locally known, and we also need to share the error between the layers. And there is no principal way to do that, and we have tried different things, and it's really art of parameter tuning, fine tuning. And we have shown that DAREK is better than GP and ensemble. So what I'm going to do next is that I'm going to discuss about Korkova's Kolmogorov network, or KDAREK. We use a hybrid approach that combine MLP and Spline together. So it's kind of take a leverage of both of this architecture. And we are going to enforce the Lipschitz constant for MLP using a spectral normalization. So instead of like calculating the Lipschitz, we enforce it for the MLP block, and it kind of mitigate many of the hyperparameter tuning. And I will show you that it's more computationally efficient even than DAREK, and it's better than GPN ensemble too.
Mhm.
Uh,
One question I have before you go deeper, in this spline neural network is pretty interesting actually. So because you're changing the activation function here, right? So you're using spline, but then the question here is, computation is one thing, but uncertainty you can fix at different layers, or is it only at the end? The aggregate uncertainty. Can you fix the uncertainties coming from the spline neural network at different layers, layer by layer? Is that possible?
Yes, that's actually what we have done.
Oh,
So it's all, you do the training, and you could do this like error calculation even in post training. Is that, you assuming that you have some hyperparameter like Lipschitz and how error is shared between the layers,
mm,
or like you can do some pre-processing, find the values, numerically, or via different other methods that we have used, like heuristic. Then you can use it to kind of like propagate error through the whole network.
I see.
That's the main result. That's the main theorem. Yeah. Yeah.
Wow. And you have published papers in this space? Yeah.
Yes.
Yeah.
So we have two. One is like in ICASP,
Mm.
and one is in Asilomar. And then we are sending two journal based on them,
Yeah,
maybe
interesting actually. So,
yeah.
yeah, I have not used spline neural network. So it's interesting to see how you fix the uncertainty. Yeah.
Yeah. So we focus on uncertainty here, but there are many works. Like for instance, I know you're interested is in like imaging and like
Image
vision.
translation. Yeah, yeah,
Yeah.
it's what I do. Yeah. Mhm.
Yeah, I didn't mention this here, but we didn't study this yet. But there are like works quite respected that they use like some spline in the neural network, and
Mm.
they could make very good like classifier.
Yeah, yeah. In fact, that's where I was going to go to. Yeah. So not only translation, but also we do classification.
Yeah.
So this is mainly for the cancer detection. So, which is pretty hard, by the way. So, yeah,
Yeah. Yeah.
to get it accurate. Yeah.
But I think it's depend on a little bit of like the physics of the problem, and
Mm.
like is spline is going to be a good fit or not. I think
Yeah.
for like 3D face recognition, because the geometry in the world is such that spline is a good fit.
Mm.
And I think in that case, the question would be like for cancer detection is also a spline, because it kind of like limits, right, the
Yeah.
geometry that you are representing. Is a spline a good fit or not?
Yeah.
Yeah, yeah. So this other work, it's called Korkova, after a mathematician from Czech Republic. And so the idea here is that instead of like just stacking layers of spline on top of each other, we are going to first project the input using MLPs to higher dimensions. And we are going to doing that using a spectral normalization, like ReLU-based MLP. And when you do that, you do the spectral normalization, you limit the weights of the neural network such that you have a Lipschitz constant, pre-decided Lipschitz constant based on the normalization. And then we are going to combine the output of these like MLPs when we like project the input to higher dimension, and we are going to go to the feature. And then after that, we put the spline block, that the PPE that I just discussed about it with you. And we are going to sum of that, and we are going to have the prediction. So basically the idea is that you project your input to higher dimension, you sum it, you go to the feature space, and then you apply the spline as a,
Oh,
yeah. So the good thing is that because you force these like MLPs to have Lipschitz constant, you can calculate the uncertainty in the features. And then after that, you can use this spline theory that I described to you to have the error for the whole network. So again, we use our propagation theorem but much more simpler in this case because you have a given Lipschitz constant and you have only one layer of spline at the end to find the error of the whole network. So what happened is that, you know, the output of the MLP is going to be the knots of the spline. And, you know, so we have like this initial data for the MLP, the input, and using the Lipschitz constant, we can find the error, a linear error here. And then we have again the block, the PPE block from Spline as the last layer. And using the propagation error, we can find the whole error in the network. And again, this is the similar example that I showed you in the past. You can see in the left that KDAREK, COCOVA's can, in terms of on-site quantification, it does similar to DAREK, but it actually results in much better computational complexity in both like training and inference time. And actually calculated this computational complexity, you know, mathematically too, if you are interested. And there is like an amount of data that if you surpass this like neural network, Spline neural network are going to work better. And let's look at that some real data. Again, I wish I have the imaging classification data, face recognition too, but yeah, I don't have it today, but maybe in future I can share it. But let's look at that 6 real world like regression data set from UCI. It's like red wine, white wine, and real estate valuation. So we are going to look at that RMSE, which is like pretty standard, right? Mean root square error. And I'm going to also define a new thing called violation. And by violation, I mean that I'm going to report the percentage of the time that a ground truth label is going to fall outside of the predicted uncertainty bound. So I'm going to do training, then I'm going to look at the test data. And then I'm going to see if when I look at the test data label, is it going to fall in the confidence interval that I have or not? And that's going to be, the percentage is going to be the violation. And so for GP and ensemble, we are going to look at that 3 sigma standard deviation interval uncertainty. And this is going to be the data. MLP can, the RMSE you can look, but they don't have any violation because they don't do uncertainty quantification. But we can use that GP, DK here stand for DAREK, KTK stand for Korkova DAREK, and ENS is ensemble, and it consists of 5 cans. So ensemble, again, is not distance aware. And as you can see, in terms of RMSE, sometimes we achieve the second best, or in general, for all of them, it's very close to the RMSE of like an MLP or a Gaussian process. But when you look at violation, again, MLP doesn't provide a violation percentage. GP and ensemble, you can look at 3 sigma, but we are going to outperform the other model much more. Almost we have like 0 in real data in terms of violation, because we look at the worst case uncertainty error. So this is also the performance of this model in real data. Yeah. So I just want to switch gears on talking a little bit also about inverse problems and how neural network are going to help us to solve inverse problem. How much more time I have?
Well, according to the scheduled time, another 7 minutes, but we were trying to see whether there are questions from the audience, and maybe we can take few questions now before we go to the inverse problem. If there is any pressing question from other people, yeah, you just unmute and ask a question. So anybody has a question so far?
Yeah, Lalit, I have a few questions.
Yeah.
Give me a few seconds. I'll get back to my computer here.
Oh, okay. Thank you. Yeah. Yeah, let's do that, because then once we go into inverse problem, it will be a separate topic. Presumably it's still related, but slightly separate, right? Let's see. I mean, this is actually very interesting. The spline neural network looks like, because you are able to find the uncertainties at each layer. That is something I've never seen, actually. I mean, I hadn't heard of that. And also, if you can do the classification, you know, I will give you some data I'll come once and I'll give you some data, and then we'll see how well you can do. Even the self-learning part, if there is a way you can bring the self-learning into it, where you have no knowledge of the classifier, like objects, we don't know what it is, but just find the objects, and then we can put in some other knowledge to identify what those objects are. So
Yeah.
we will connect after this. Yeah.
So
Okay,
I
you
have
can ask a question. Yeah.
So I have a question on slide 41,
Oh,
and I apologize. I'm asking the question now because I have to leave in a few minutes.
Yeah.
So you developed the algorithm, and did you test these in software, in custom hardware, or just mathematical model?
So we first developed a mathematical model, and then we like coded in Python, and then we use this like real data to test it, but we didn't do any hardware yet. Yeah.
Okay. Is
Yeah.
there any interest to move this into hardware?
Yeah, that would be great. Like, yeah. Like
In other
design
words,
us-
let me ask different. If once you have developed the algorithm, is there a platform you can deploy it effectively today, or do you need custom hardware or some domain-specific hardware or architecture to run it?
Yeah, I think it's an interesting problem to think about, and I'm sure domain-specific hardware always could increase the efficiency. Yeah, I haven't thought about it, but it's a nice problem.
Okay, thank you.
Yeah,
Hmm.
you're welcome.
Alkesh, you had questions, so let's address
Actually,
that.
Doreen read my mind. I was asking the same question. The real practical, application. You mentioned that Boeing 747 Max and autonomous vehicle and efficiency, right? This balanced computational efficiency. So that was my question. Exactly, Doreen asked that. Are there any practical implementation of this proposed methodology, right?
Yeah, so in terms of like the first part of the talk, the GP, yes, there are like practical implementation. If you are interested, I can send some papers, that my former colleagues, Nikolai Atanasov and other, they have actually implemented this algorithm and its like extension on real like embedded hardware, on robot, in a car-like robot. Actually, they also consider the case that you don't know also the uncertainty. And yeah, they have implemented this. But for the Spline one, it's very recent. We just did it like we are still like doing the journal version. So yeah, I think there is also a plan there to do embedded hardware, but we haven't done it yet for this part. Yeah, and then I have very good colleagues, there at University of Maine, Vikas Dehiman. So yeah, we have been working from the time that I was a PhD student and he was a postdoc at UC San Diego, maybe like 5 years, 6 years, we are working together now. And so yeah, if you have like a specific data or anything, just you can like share it with me. I will share it with him too, and we can look at it. And Masood is like Vikas' student, and it's we are very nicely collaborating on this. Yeah.
Yeah, great. Thanks. I have a second question. Let me ask here. I'm teaching power system stability and controls. So some of things are interesting that apply. I'm wondering, you may have any opportunity to work and apply these methods on power system controls?
So I think I know some results from PNNL, Pacific North Lab.
In Washington State.
Yeah, that they use like maybe Gaussian process and alternative quantification for like control of the power systems. And so I at the beginning I was talking about like good examples of like how to apply, learning safely to control system. It was like data center cooling by Google, but also like I think PNNL also have some very interesting result for power networks, as far as
Yeah.
I remember too. And yeah, I haven't done it directly, but I have seen those results. If you want, I can look at it more closely and share it with you. Yeah.
Yeah. If you have anyone, in your professional circle working on power system areas, power engineering, if that we would appreciate, you can recommend that later
Okay.
on. Yeah. To one comment, it's not a question rather than comment. You might know Dr. Ralph Killing from UC San Diego. No, from Scripps Institution of Oceanography, right?
Yes.
Hmm.
Yeah. I think his name is.
Ralph Killing.
Yeah, I think he's. I heard his name for sure. Yeah, it sounds very like familiar. Yeah.
Yeah, he's the inventor of that killing curve, basically. The climate, I think, climate related to climate, actually. The reason I ask you is, Lalit, I was inviting him for our assignment lecture. He's very
Oh.
well known on this field.
Yeah. So
Yeah.
if you think he's
Yeah.
yeah.
Other one is the Zachary Pesnek. You might know around the same time you were in UC San Diego.
Yeah. I
Yeah.
think all of them like yeah. I know the names, but I don't remember now. Yeah.
Well, thank you. Zachary was around same time. He was also did PhD from the same school around same time, and he did work on this power system area, actually microgrid and Zendi. He was our PES chair last year. He's in Albany area.
Oh, that's nice. Yeah.
Great, thank you. Yeah. Go ahead.
So yeah, because I interrupted, I mean, some people might want to leave, but I can stay for another 10 to 15 minutes if you want to continue. Yeah, I liked some of the things you presented has some relevance for what I do. So yeah, and you heard from Alkesh as well as Dorin about the relevance. So yeah. You want to continue? Yeah, people can stay on for another 15 minutes and then we'll close.
Yeah. If you can share, some papers or references later on, that would be great. So we can take a look at our own time. But maybe you can make a comment on, I'm curious about your remark on the Boeing and autonomous vehicle exactly. So what was that?
Can you hear me or?
Yeah, I can hear you.
Yeah, so the Boeing example, yeah. So when you all of this, unfortunately, all the data is not available. But when you look at just the report that DeepMind has written for cooling center, you see like they have like all the layers of safety, and then there is also like at the last resort, there's also human intervention. And then there is like a policy, like a general policy that you can always switch to. And they do like a formal method, safety verification. And, there is 1,000 sensors there. But the Boeing, I think they push AI there, unfortunately, and they have only 2 sensors. I believe one of the sensor was hit by a bird. Again, all of these like classified, but just by the, you know, news articles and some, blogs that the companies has written out there. And then, one of them was hit by the bird, and the pilot wanted to do something, and the confused AI was saying that, oh, I'm going to rewrite it. And they have like the fight. And in some cases, there was like cases that pilot were able to, rewrite it and safely land. And there was like, I think maybe 2 or 3 cases that it didn't work well. And yeah, and then at that point, I think Boeing figured out, oh, maybe we should like call back this.
So yeah, that was safety issue, right? If pilot intervention happen, then this will eventually adapt and override that intervention.
Yes, yeah. That was the issue. It doesn't have uncertainty quantification. It doesn't have enough sensor. It has 2 sensors. You know, it's a sad story, really, right? It's just like
Yeah, that was a big in the news, right? Boeing
yeah,
747 Max. Yeah.
yeah. Sometimes I think people try to push AI too much, and it's like kind of like reckless engineering, right?
Yes, yeah. Thank you for your insight.
Yeah.
Okay, so you want to continue? And well, because you came prepared for that material, so we are interested to hear that. Yeah.
Yeah, sure.
Yeah.
I will try to do like 15 minutes. Yeah.
Yeah. Sure.
And then so let me talk about like inverse problem and how like learning label method could help to solve inverse problem. So one of the famous area to look at inverse problem is like underwater acoustic. So you have like forward problem when you look at underwater acoustic is that you want to understand how sound is going to propagate in the sea. You have like some parameter X, and you want to see like what kind of signal you receive on the hydrophone. And by the way, hydrophone is the water version of microphone, underwater version of microphone, and you have like arrays of them. It's called VLA, vertical linear arrays sometimes. And then you also have like an inverse problem. An inverse problem is that you want to infer geometric, oceanographic, or like geoacoustic information from acoustic signal. So you have like a data received acoustic signal on the array, and then you want to say, oh, what was the parameters of the medium that this signal has been communicated in. One of the toughest problems is geoacoustic inversion, and the aim is to characterize the undersea environment, like seabed layer, sound speed, and density of the layers. And when we do that, it's of great interest because when we know what is the bottom of the ocean or a lake, it helps us to predict how sound is going to propagate in the bottom limited environments. And application is important for Navy because it helps for sonar performance forecasting. Also, it's important for noise population at sea because humans are making more and more noise and like polluting the ocean, and it has an effect on animals and ecosystem. So in this problem, geoacoustic inversion, you have a source that transmits a signal, and they choose specifically the frequency between 50 to 400 hertz to ensure that the sound is going to penetrate to the bottom layer and reflect back. And it's going to be measured on the VLA, vertical linear array of hydrophones. And Y here is going to be the received pressure on the microphones, and F is going to be the forward acoustic model. There are many ways to make this forward model to calculate it numerically. It's very complicated function. One of them is called Kraken, which is used by Navy and researchers either at Escape Institute of Oceanography or Woodhill's Institute. Yeah, and epsilon is the observation noise here. And the aim here at this problem is that you receive this signal, you have a source that you have a ship that tow your source, you send the signal, you receive it on the VLA, it's going to penetrate to the sediment mudstone because of the frequency that you choose. It come back and you want to know what is like this parameter M is. And because this forward map is very complicated and the number of things that you don't know is much more than the number of array element that you have in the array, the inversion is, as you know, in many other areas too, it's usually ill-posed. And, you know, we can, again, look at the Bayesian approach to inversion. And we can like formulate a posterior distribution to enable uncertainty quantification and look at that the diversity of different solution. Maybe instead of one mode, you have 4 mode. Maybe you have some maximum that are close to each other. If you look at that, what is the distribution over your unknowns, it could give you so much more knowledge. But the issue is that it's very hard to sample distribution in general in high dimension, including posterior distribution. So instead of the art method used by researchers and like practitioner is the Monte Carlo Markov chain. But it's very good, much better than naive grid search. But again, they're going to suffer from suffer from computational complexity. I think the most that you can do is like 10 number of variable unknowns. And now Sometimes when people want to do this like acoustic inversion, maybe they need to let the computer, to run for, even a good computer, run for a week to be able to do this. But now think about if you want to do any sort of like sensing in a robot, in ocean. So usually we do it like manually. It's cost and work intensive, but in future we hope that we can do it, on a platform, on a robot, and if we're able to do that, then we can also think about like active information acquisition, how the robot should move to gather the most amount of information about the environment and parameters that they want to estimate. So this is the platform that I used to work at Scripps with Florian Meyer and Bill Hotchkiss. Yeah, but these are the platform that I have right now at RIT. So we integrate hardware, computation in NVIDIA Jetson, but it has a lot of limitation of computation power. Also, the battery is a limitation. So like making estimation algorithm that are attractive in terms of like computation cost, it's of great interest. So what I did here is that, we propose to use invertible neural network in this case, study the performance of INNs. It's a very recent work, and also I've been working on ongoing work on how to do this like symbolically, and I will tell you about the benefits. So the whole idea is that you wanna use a normalizing flow to do some sort of unsupervised density estimation and generative modeling. So you have data xi from your distribution. It could be a posterior distribution, and your goal is to estimate the distribution over p of x. And the idea is that you introduce some variable called latent variable z, which its distribution, and you are going to train a invertible map t that map x to z. And your aim is to find a mapping T that in some divergence, maybe K divergence, Jensen-Shannon divergence, Wasserstein distance, kernel MMD, it's going to ensure that the probability of PZ and P of TX is minimized. If you do that, because by ensuring that the divergence between Z and TX is minimized, because it's invertible, you can show that you can also establish closeness between X and T inverse of Z. So in this case, you can run the network backward and look at that T inverse of Z and estimate the posterior PX. And there are many ways to use this concept of normalizing flow to solve inverse problems. So one of them that we are going to look at is going to be called invertible neural network. It has been around, I think, since 2019. And I will let you know what is our contribution here. It's like theoretical guarantees that are practical, and also looking at the ocean example. And so the way that we are going to do it is that we are going to augment the label data y with the latent variable z. And you can think about like a camera that you take an image from 3D space. You have a 2D photo. The 2D photo kind of lost some of the information during the forward process. So to counteract the loss of information during the forward process, we can like make this latent variable z. And the choice of information, the choice of distribution on latent variable z is very important. Usually people do like Gaussian or mixture of Gaussian. So that's why normalizing flow is important for solving inverse problems. Some of the information is going to be lost, and you model it using a normalizing flow, and you augment it with your label data. One way is to just augment it. The other way is to make the data, a following paper from the same author that came up with this, is that you kind of condition the network on this data. It's called conditional invertible neural network. But let me move and tell you what we have done here. So once you train this network, again, you can like generate data from Z and let the network run in backward, and you solve your inverse problem, and you have a estimation of your posterior. And you can use values like supervised loss and unsupervised loss here. And there are many ways to define this. One thing that we notice is that this large class of divergences, it could be unified in a framework, in a variational framework, either for like training normalizing flow or for like invertible neural network. An example that we can use here is like a regression cost, least square cost for label data. And this is going to be F divergences, variational version of the F divergences. Here, GN is going to be the critic class, and F star is going to be the complex conjugate of F. So this is based on a paper called FCAN. Yeah, it's inspired by idea of like generative adversarial network and F divergences. So these neural network are a specific class. They have like there are a subclass of deep neural network, and they have this invertibility, and this invertibility came from like a specific design architecture. Is that we are going to learn a mapping between input and output that is bijective, so invertible. And we want to have such that the forward and inverse mapping are efficiently computable. And also we want to have a tractable Jacobian, hopefully even in the closed form solution of Jacobian, such that once we train, we can like find the closed form solution for the estimated posterior over like X, which is going to be T inverse of Z. And this specific property is going to arise from their architecture. And there are many ways to design like neural networks that are invertible. One of them is going to just look at that they're like not a regular neural network, a neural network that is like modeled like a triangular, and it has a limited architecture. Another one is that you can use residual neural network. In fact, it's very general architecture, and it's called like IResNet. And you can ensure that the neural network whole neural network is invertible if each block has a Lipschitz constant less than 1. And this method is very stable and it's very general architecture, but it's more computationally demanding because you need to approximate both the inverse and Jacobian using fixed point theorem. And then there is like the coupling base that I'm going to discuss it in more detail, that kind of like balance between computational efficiency and expressivity, but it's less stable than IResNet. And they are proven to be universal diffeomorphism approximator of functions. And it actually gives closed form inverse and Jacobian. So the way to design this invertible architecture is that, you have your data, you are going to break it to 2 parts, and you let the second part go through the general neural network mapping S1 and T1 and get multiplied to first part. And then you are going to do this, let the same thing for V1 and multiply and add it to V2. And you have like this equation. And again, S and T could be arbitrary neural network. And the good thing is that when you do it in this way, once you have forward, you are going to have inverse naturally. And it's a very smart idea. I think it's from a paper in 2016 called GLOW. Is that you just reverse the direction of arrow and replace the plus with minus and multiplication with division. And you are going to get the inverse automatically. So notice that when you invert the blocks, you don't invert the function S and T that could be general neural network. And if you make your neural network from these blocks, it's going to be invertible at the end because each block is invertible.
Wow.
Yeah. And there are like performance guarantees. There are not many performance guarantees on these networks in the literature in terms of like accuracy of past estimated distribution. So what researchers have been done is that they are going to like kind of incorporate normalizing flow to MCMC, to the Monte Carlo method, to accelerate Monte Carlo method, at the same time use the theoretical guarantees of MCMC. But what we have done is like take a totally different approach. We say that, okay, we want to have the efficient learning enabled inference, and we want to theoretically, guarantee the performance. So look at the posterior inference in INN, the quality, and also the quality of generative modelings in normalizing flow. So I'm not going to go to the details, but this is the main theorem that we proved, is that if you like approximate posterior using this method, the Wasserstrand distance of 1 between the actual distribution and the estimated distribution is going to be less than equal to Rn to the power of A divided by 2 plus A. So here Rn is a sequence that tends to 0. A is the moment of distribution on X. And W1, I say what it is. And this notion means that it's suppressive some multiplicative factor that depends on A. And we also like simulated the theorem that we have proved in practical example too. And you can see it has a sort of polynomial behavior at A that it could be seen in the simulation here too, given that Y here is logarithmic scale. So let us look at the application of this in geoacoustic inversion. When you assume that we only do not know two parameters, M1 and M2. We know all the other parameters for simplicity. M1 is water depth, and M2 is sound speed. And so when we want to solve the inverse problem, we want to like augment this data with the noise, because we could also assume that the noise that you received in the hydrophone is not known. And so you have the measurement and you have the latent variable Z. And we have some prior knowledge on the water depth and sound speed, and observation noise is assumed to be a Gaussian. And we actually look at that the setup of our experiment for geoacoustic inversion, SOLX 96 done in San Diego, close to Point Loma. And when you look at that performance, for instance, using KL divergence or Jensen-Shannon divergence, it's very good. The red here is the value that we want to estimate, and these are the posterior that we estimated. It's not actually the posterior, just the estimated or terrain posterior. And I told you at the beginning, sometimes it takes like a lot of time to solve this problem. But here, when we like pre-terrain a normal neural network that is invertible, the real we get the near real-time posterior inference of 0.006 per thousand sample. And it's like much more computationally efficient than likelihood-based MCMC, because in MCMC, you need to calculate the likelihood. You need to run Kraken every time to get your likelihood and then get a sample and you keep it or not to make the posterior. But you can like terrain this network offline and use this pre-terrain one, to do the inference. And there is no magic here. The speed of just come from like shifting everything offline. And no single method is better, it depends on application. These are well like great in terms of computation time, but they exhibit sensitivity in design parameter. And we have to like employ a 3D structure estimator to find good set of hyperparameter to get good results here. And I'm just going to also like, this is an ongoing work. For the sake of time, I'm not going to talk about it anymore. But I just want to mention that we are also working on like making this like symbolically interpretable, like making, instead of like using ReLU for S and T network, we want to use something called EQL, equation learning network, when we replace the activation function with function that are from physics. We find like from the physics of problem, these are like good function. And then the aim is to like have an analytical formula for both forward surrogate modeling and for the inverse direction. So we can see, how much each component of data or latent variable is contributing to solving the inverse problem. So we are at the moment only at toy examples, but here is like a Gaussian that we want to take samples at 0.0 and 3. And this is when you try to solve this Gaussian using like normal Gaussian, using mathematical equation. And we have like generated this like network, which is very complicated to train. But you can actually do it efficiently, but it's required fine tuning, hyperparameter tuning, but it can actually give you the equation. So it's a neural network that can do like solve inverse problem analytically, and it's very nice. Yeah.
Yeah.
Thank you.
Thank you. Yeah, this is amazing. And one question on the invertible neural network is, you know about cycle GANs, right? They're used in image translation, so you can do forward and inverse with the GANs. The results you get with invertible neural networks must be very similar to cycle GAN, right? Or is it going to be better, or computationally more efficient, or network is simple, or those sort of things?
Yeah, I think the only benefit of like normalizing flow is that unlike GAN or like diffusion model, you have potentially, for instance, you use coupling base, you have a closed form formulation for the estimate output of the neural network, you know. So that's the great thing, because this mapping
Oh,
are
in
like,
the invertible neural networks, you have closed form solution, you're saying.
yes, yeah, because
Oh,
you
I
know
see.
the distribution of Z, and you know the Jacobian, you can calculate it efficiently. So
Oh.
whatever estimate you generate here, you are going to have a closed form solution for it.
Mhm.
And
I
that's the reason that actually we are been able to, you know, have like theoretical guarantees. You know, oh, this is going to converge. But for diffusion model or for like GANs, you know, it's yeah, I need to look at it more closely. But
Yeah,
I
cycle
think,
GANs are basically forward and inverse. You know, so you can go in the forward direction. You can also come back in the reverse direction. You know, so that is the principle of cycle GAN. So yeah, and
Yeah,
that was because they use that for training image translation networks, daytime to nighttime, nighttime to daytime. You know, that sort of thing. Yeah. So yeah, good. I think this is good. I found very informative. Are there any questions to Professor?
yeah, I actually have a question. You know, actually, was talking about the DAREK is computationally efficient than the Gaussian process, right? And from a software perspective, I'm a software engineer. So from a software perspective, are there any open source libraries or frameworks that we can you recommend to start with to experiment with DAREK?
yes, actually we have, like, if you look at both of these papers, there is like the GitHub is available there. All the, you know, we even have like website, you know, Vikas and Masood also did a great job. We have also like website for this, and there is like, it's on Masood GitHub, so you can go and like both of the code are open source. Yeah, you can use it on any data that you like.
Cool.
Yeah.
Okay,
Yeah.
cool.
Yeah, thank you. Do you have? Can you share the slide deck, or maybe we have recorded already, so we could.
Yeah, I could do that. Yeah, for sure.
Yeah, because that has references, so that way our folks can look at GitHub through that mechanism. Yeah.
Yeah.
Great.
Yeah, I could also share the GitHub link. Yeah, I will do that.
That will be helpful. Yeah. Thank you, Professor. This was very informative, and for me, I find a couple of them very useful. So I will bring some data when I meet you next. Maybe you know, in April, end of April or something. I will let you know when I'm available to come there. In person, I'll come to RIT, and then we will chat with some actual data. So
Yeah.
these are the, you know, medical data. So because I find value in especially spline neural network, and maybe in the invertible neural network as well, but I have to understand that a little bit more. So yeah. The value.
Thank you.
Yeah, good. Thank you. Alkesh, do you have any other question?
No, not a question. But a great lecture, Professor. And
Thank you.
my area is different, but control system is everywhere, right?
It's used everywhere.
If we can learn and apply those methods in different areas.
Yeah.
Murali is online. Murali, do you have any questions? He's going to be our treasurer. Alkesh has to send him a note. Just recently joined as an officer with us.
Yeah, Murali, thank you for your interest. And I'm traveling this week, so we'll catch up when I come back home next week.
Sure, Akhilesh. Yeah, thanks for having me here. It is interesting. So, like all these days, I'm working for a service-based company. Most of the things are like AWS cloud, and most of the things are like service-based, right? I remember like when Mohammad was explaining about all these models, I remember like the project which I did for my engineering, right? So I worked on like a hidden Markov model, which is basically used to identify the phonetics. So it was exciting. So like since I'm in this forum now, it looks interesting, so that I can dig most of the things like which I learned in my engineering and my master's. Excited to have in this forum. Thanks to
It's good. I really like it, and also it's computational intelligence. So all AI can be put into this, but we need to have some application focus. It's not just the theoretical side. So yeah. So thank you once again. And yeah, in person would have been a lot more exciting, but this is okay. No?
Thank you for for having me. Yeah.
Yeah, thank you for your time. Yeah.
Thank you.
Thank you.
Bye.
Bye.
Thank you.
Thank you. Have a good one. Bye.
You too.